univariate case, so we are on the Riemann sphere, and we can ask whether it is possible to find a Fuchsian differential equation in the classical sense, which has solutions with correct singularities and correct monodromy. So because our monodromy is so simple, it is simply generated by permutations, it is kind of natural to call this a discrete version of the Riemann-Hilbert problem. So there is also, of course, the 21st Hilbert's problem about monodromy and whether it's possible to realize any monodromy group as monodromy representation of a Fuchsian system of differential equations. And it has been thought for almost 70 years that this problem was completely solved by Lemel in 1908. However, in 1980s, it became obvious that there was not really a gap, but also a wrong class of systems of differential equations in which this problem was solved. And in 1989, Bolivarov constructed his counterexample. So the 21st.
So it was believed to be solved.
Yes, right.
There was completely a mistake or misunderstanding of the problem.
Well, it was. Yes, there was a mistake, but the proof worked. Well, to the best of my knowledge, the proof worked, but in a different class of systems, for a larger class of systems. So, as opposed to Fuchsian systems of equations, Lemel actually solved the problem in the class of systems with regular singularities. And there is a difference when we speak of solutions to systems of linear differential equations. So, the proof was okay, but in a larger class of systems of equations.
So it solved a different problem, not the original problem?
Yes, yeah. Essentially, yes. And in 1989, Bolivarov has constructed his counterexample. So this problem now has a negative solution by counterexample. Okay, so for the rest of my talk, I will be focusing on this. Yes, so first of all, let me mention the theorem obtained jointly by Larison and myself, which states that it is, of course, impossible to give a positive answer to this question. So whenever you're described a finite set of singularities and discrete monodromy generated by permutations, it is always possible to find a ordinary differential equation, a Fuchsian differential equation with correct singularities and correct monodromy. And I'll be focusing also on some computational issues, and in particular, I will recall a result obtained by Eduardo Catania, Carlos Andrea, and Alicia Wittgenstein in 1999, which gives us the determination, the exact formula, very simple and concise formula for the determination of a function defined by a generic algebraic equation. Namely, so let me put it this way, the order of the differential operator, the theoretically always existing minimal or optimal linear differential operator with polynomial coefficients, whose solution space is spanned by the branches of a given algebraic function defined by a generic algebraic equation. So such an operator always exists, just as I explained earlier, in particular by a number of examples. And its order, it is the determination of that function. This is in fact an equivalent definition of the determination. And that determination is this. It can be computed as m-1 plus the integer part of m1 divided by m-1 if the greatest common divisor of the exponents is 1, or otherwise it is simply this equation. So this is the explicit formula for the order, for the smallest possible order of a linear differential operator with polynomial coefficients satisfied by the solution to a generic algebraic equation like this. So now you can actually use it and develop an algorithm for computing such operators. So let me show you a theorem, an algorithm, and a number of examples. So it turns out to be helpful to look at the residues, of the reciprocals of powers of the polynomial defining that initial algebraic equation. And we scale it by some suitable rational functions. And we look at the ideal generated, the ideal simply in the polynomials with the generators as 1 and so on as m, generated like this. So for any k, we can define such an ideal. And it turns out that the coefficients of that optimal differential operator for an algebraic function, they are always in the syzygy module of such an ideal. And this naturally leads to the following computational procedure for defining such an optimal differential operator. Namely, we compute the basis of such an ideal, and of course we simplify as much as possible and as early as possible by using in particular the Vieta relations. And then we compute the Grobner basis of what we got. And this will eventually give that elements of the syzygy module of that ideal. And we'll end up with the optimal differential operator for a given algebraic function. So let me try to clarify this by means of another point of view and also a bunch of examples. So just as I mentioned before, there is a commutative way of looking at the differential operators, differential polynomials defining complexity classes. So now here in this example, we're looking at non-commutative elimination in the Wien algebra of linear partial differential operators with polynomial coefficients, and we apply this to the simplest example existing. So we simply look at the second order algebraic equation. Now all the coefficients are here and generic, and the corresponding Gelfand-Kaplanov-Zielinski system. This is probably the simplest possible version of the Gelfand-Kaplanov-Zielinski system of equations, or at least I can't think of anything even simpler. It is defined to be the ideal in the Wien algebra of linear differential operators with the generators x1, x2, x3, x0, x1, x2, and dx0, dx1, and dx2. And the theorem states that the classically known theorem, that statement on the solutions in the Nielsen class, or rather for differential operators for the functions which are in the Nielsen class, and this is of course in the Nielsen class, it states that there always exists a polynomial coefficients differential operator whose order is equal to the determination of this function, that is 2, which only contains derivatives with respect to x0. And naturally it does, namely we can do it in this example by means of non-commutative elimination in this ideal. So if we take that operator to be the following linear combination of the generators, p is equal to this times a plus this times b plus this times c over here, then we end up with a multiple of that differential operator. So this is.
It also follows from the classical theorem of Comte that a algebraic form a power series.
Oh yes.
Satisfy differential.
Yes, by all means. For sure. Yes, that was a very good point. Thank you. Right. Now let me show you another example of annihilating differential operator for the roots of the fourth order differential equation. So we now specify some of the coefficients to be equal to 0 or 1, and we'll look at the function y defined as a function of one complex variable x by means of this algebraic equation. So this optimal differential operator has the following form because of the theorem by Kaptani, Andrea, and Wittgenstein. This determination here is equal to 3, namely the exponents are relatively prime. So we have this line over here that has to be used. And we expect a third order, now ordinary differential operator with polynomial coefficients. And it is as follows. So this is the optimal differential operator for the algebraic function defined this way. Well, those operators are quite non-trivial to compute, and we have developed a package, a mathematical package for computing such differential operators. And of course, in that computation, you have to completely avoid the actual roots of the algebraic equations because they are complicated and very difficult to deal with. Well, you can, of course, express them through theta functions or through hypergeometric functions. However, computing the determinant, the Brodsky determinant, is quite a task in itself, and simplifying what we got is even harder. So, of course, we proceed directly from the initial equation to the optimal differential operator. And this is, by the way, quite a popular avenue of research. For example, there exist commands in Maple, algebraic to differential, I believe, which does the same thing.
Yeah, GFun package.
Yes, in the GFun package, exactly. And also in Magma computer algebra system, there is also a command which does the same. So we have developed our version of somewhat an original version of that procedure, and it does well on many algebraic curves. So using that, we were in particular able to observe the following interesting fact. So here, the leading coefficient in this differential operator, it is of course the polynomial whose zero locus naturally contains the singularities of the function defined by this algebraic equation. So this polynomial over here is, of course, the discriminant of that algebraic equation. However, in this case, the leading coefficient is not just the discriminant, but we also have to multiply with this affine factor. So this is some kind of parasitic factor, which does not have so much to do with the singularities of the solutions to the initial algebraic equation. And what is interesting here is that this lowest order term, this polynomial over here, well, it is quite a different polynomial. However, it does have the same Newton polytope. And this is one of our conjectures. So really intensive computer experiments. So I really have to mention calculations because this is an experimental mathematics seminar. So really intensive experiments show that the Newton polytopes for that, so to say, essential or apparent factor in the leading coefficient. So if we forget about the discriminant, then what is left is that factor, which is in this case simply that affine function, and the Newton polytope of the lowest order term that they coincide. But this we haven't proved yet. This is still a conjecture based on numerous experiments. Right, and well, just as I mentioned, it is possible to use different functions for defining complexity, and we sometimes get different complexity classes, but for all arithmetic operations, the chain of complexity classes is the same. Right, so now the connection to hypergeometric. Of course, hypergeometric is a natural class because up to some unessential changes of variables, up to some scaling of some sort, up to mononomial changes of variables, algebraic functions defined by means of generic algebraic equations are hypergeometric because of the result of Mayer, for example. And there is also the classical Mellin system, which was initially designed by Mellin himself, along with Mellin-Barnes integral for solving algebraic equations in terms of hypergeometric series and estimating domains of their convergence. So let me simply recall that a system of differential equations of hypergeometric type is typically defined by a matrix and a vector of parameters. So we're looking at a matrix A with integer address and of maximal rank, and a vector and a complex vector of parameters. And we'll define the thetas. So thetas are the Fuchsian or the Euler derivatives to be xi to the xi for x being a complex vector in the complex space. And well, not really the Gelfand-Kaplan-Zelinsky system, but rather its dehomogenized version. So without any homogeneity relations, if we make a change of variables to get rid of them, then what we end up with is a rather classical system of partial differential equations of hypergeometric type. So we simply define differential operators in this way, and we're looking at the differential operators hi to be defined as xi pi minus qi. And well, we define the Horn. Well, this is very coherent with the classical definition given by Horn himself. We define the Horn hypergeometric system of equations to be the left ideal in the Wien algebra of linear differential operators, linear partial differential operators with polynomial coefficients, to be defined, to be generated by these operators h1 and so on, hn. Of course, the branching of solutions to such a system of equations can be very complicated, and this is in fact an unsolved problem. How to actually compute the monodromy of such a system of equations when it is holomorphic. So for example, just to give you a flavor of how it can look, we can look at one of the classical systems, the output F2, and it is defined by these operators. So I mean that the system is defined by this acting on f should be equal to 0, and by the second operator acting on the unknown function, and that's also equal to 0. And if we specify all the parameters to be equal to 0, then we get the following basis of analytic solutions of finite complexity, by the way, finite complexity, which go as follows. And in this case, it is possible to compute the monodromy completely. So we have these monodromy matrices, and everything is clear in this case. However, if we specify the parameters to be different, if we choose this set of parameters, then we actually get a polynomial basis of solutions. So this is another package developed by us for effectively solving such a system of equations in the class of polynomial functions. And well, for computing complexity, it is natural to ask whether the solutions can be as simple as possible. And this is a counterpart of the notion of the maximally reducible monodromy of such a system of differential equations. So maximally reducible monodromy means that the whole solution space is simply a direct sum of one-dimensional invariant subspaces. And this is a theorem due to myself. It was possible to characterize all bivariate systems of equations with maximally reducible monodromy. Namely, it corresponds to the case when the initial matrix defining that system defines a configuration which is either a zonotope or the Minkowski sum of a triangle and its sides, possibly with some multiplicities. So now, skipping the examples, I will proceed directly to the corollary, which says that in that case, all the solutions have finite analytic complexity. Right, so concluding my talk, I'd like to say that this is a sufficient condition for a system of hypergeometric equations to have solutions, to have a basis of solutions of finite complexity. However, it is really far from being necessary. Lots of unanswered questions here. Thank you so much for your attention.
Thank you very much.